That was an unforgettable hour. I was very privileged to be able to do that. I will never forget that.
Down the Holy Land, you could see Israel, you could see the Tigris and the Euphrates rivers, you could see the Greek islands, Africa disappearing over the horizon in the distance, and I'm saying, the cradle of civilization is right there, and I may be the first guy that ever saw all of it laid out just like that, okay? That's stunning. That's beautiful. You never forget it.
When you get up there, the Earth looks very much alive. It's green, it's blue, it's brown, it's a living planet. And you look off the side a little bit at space, and it's the blackest black you've ever seen. And you get this feeling that we've got this little bitty planet that's a live thing going through this great big vast void out there of nothing. There is just nothing out there. And so I think you come back with this feeling that we've got a very special place here to live, and we've got to take care of it because there's nothing else out there.
The human eye is a remarkable scientific instrument, but we have also put other eyes in the sky. Remote sensing satellites. From hundreds of miles up, these satellites observe our planet and its resources. Mountains and rivers, oceans and deserts, cities, forests, and crops. Satellites scan whole continents in minutes, yet they can also pick up objects as small as a house or a boat. And they can sense more than the human eye can see. For example, they can see heat in the form of infrared radiation. Some can function at night or through cloud cover.
This is the Gatineau Satellite Receiving Station operated by the Canada Centre for Remote Sensing. Here we track and receive and process data from the Spot satellite launched by France. Let's take a look at the information inside. And we can see the data that's being played back as the satellite crosses over the western part of North America.
Satellites allow us to look at our planet in ways never before possible. Images from space help us predict the weather, prospect for oil and minerals, detect crop diseases, combat drought, and much more.
And especially in combination with some other products that we derive from the satellite image, we can put together a package which allows us as geologists to work easily with the image. Once we completed this stage of image analysis, we then put on our boots and we go out in the field like normal geologists and we collect rock samples.
We would tell the computer that those fields are potatoes, so we go from a very specific area of information to the computer classification, which gives us an overall view.
In this image of 1985, there is a difference in this area versus irrigated and a more natural agricultural vegetation here. And on the 1983 image, where it was a normal year, we can see a more uniform distribution of the colors where agriculture is healthy. One of the benefits is that we can compare then a good year to a bad year and forecast yields in a drought situation.
The vantage point of space has enabled us to learn more about the Earth and its resources in about 2 decades than we had known for centuries before. The knowledge we have gained has altered our perception of our planet forever. This perspective has done more than teach us new things about our planet. It has impressed upon us that Earth is a planet, one of a family of many others. The same technologies that enable us to study the Earth from space have also given us a close-up look at the rest of the solar system. Planetary probes have been our proxies, going where we cannot go ourselves. Some fly past the planets, some orbit. Still others land. Spacecraft sensors have transmitted remarkable images of the outer planets and their many moons and rings. They've recorded giant hurricanes on Jupiter, just as they've observed weather patterns on Earth. The journeys of these planetary probes have dramatized how large our solar system really is. And yet, we know that our group of planets occupies only a small, insignificant corner of a vast universe. A universe of many stars, many galaxies, and many more objects that we don't even understand.
From one side of the galaxy to the other side is about 50,000 light years. So if you turn on a light switch on one side of our Milky Way galaxy, you would see it in the other side only 50,000 years later on. So it's a huge system. It's a system that is composed of about 100 billion stars. So all the stars that we see in the sky, with the naked eye that we go, are all stars in our own Milky Way galaxy. It's part of those 100 billion stars, and they all move around in the galaxy, just like the planets move around the sun.
Distances between stars are enormous, far beyond our physical reach. Even light takes billions of years to cross the vast reaches of the universe. To see the stars, we have only one tool, the telescope. Telescopes allow us, in effect, to see backward in time. When we see light from a distant star, we see that star not as it is today, but as it was when the light first left it, millions, perhaps billions of years ago. Over the centuries, telescopes evolved from little more than handheld spyglasses to huge observatories. But as remarkable as these instruments are, they encounter a common obstacle, the Earth's atmosphere. The shell of air that keeps us alive also obscures our vision.
Hotel Mike, broadcasting at a frequency of 20.5665 megahertz from the University of Toronto's David Dunlap Observatory, calling Las Campanas Observatory. Are you there, Las Campanas? Over.
This is Las Campanas responding to Victor Echo 9 Lima Hotel Mike. Go ahead, over.
Hello, Ian. It's Bob here. How are things going? Over.
In terms of people relaxation, I think it's fine.
In an effort to escape the worst effects of the atmosphere, we put telescopes on high mountaintops. But even the best Earth-based telescopes are hard-pressed to see faint objects in the sky, or those at the farthest reaches of the universe. And they cannot see at all certain types of stellar radiation blocked by the atmosphere, such as portions of the ultraviolet or infrared spectrum. When Galileo invented the telescope, he used it to prove the Copernican theory that the Earth was not the center of the universe. Since then, our concept of the universe has continued to evolve with the improved power and resolution of new telescopes, allowing us to see things that we've never seen before. White dwarfs and red giants, supernova and quasars. Using the latest telescope of the times, to study the velocity of galaxies, Edwin Hubble was able to prove Einstein's theory that the universe is expanding. But how did it start? We think it started with what scientists call the Big Bang.
The Big Bang theory says that the universe started from an extraordinarily small, dense, compact state. All the matter that we see in the universe now, all the galaxies, all the planets, all the stars, everything that is or that we see in the universe was in an extremely tiny, dense state. And for some reason, that state became unstable, and it erupted, it exploded. And it expanded very, very quickly. And after a significantly long period of time, the matter started to cool down, and structures started to form in the universe. The things that collapsed out, condensed out, were either stars or globular clusters or galaxies first. Nobody really knows which one, and that's an outstanding problem in modern astronomy and cosmology.
Trying to solve the riddle of the Big Bang and other astronomical mysteries has pushed Earth-based telescopes to their limits. Further clues to these mysteries must now come from telescopes that leapfrog the barrier of the atmosphere. We've already put several small satellite observatories on orbit. The next major step is the Hubble Space Telescope.
Well, the Hubble Space Telescope is going to be the first optical telescope in space that will be a long-range observatory. It will be the first actually big telescope that will be put above the Earth's atmosphere by NASA, the National Aeronautic and Space Administration, with the attempt of going above the atmosphere so we can look at stars, at galaxies, at everything that is out there in the universe with very high precision, rather than look through the atmosphere that blurs the images, disturbs the images that we see from the ground. For example, if we look from the ground in the sky to the sky, it's like looking at anything out the window through a curtain. You just can't see the images very well.
Scientists and engineers have spent 20 years getting this $1 billion telescope ready for launch. 13 meters long, 4 meters in diameter, the Space Telescope weighs about 11,000 kilograms and contains a 2.5-meter primary mirror. When shuttle flights resume, it will be launched into an orbit about 500 kilometers above the Earth. It will be able to see stars 14 billion light years away. In contrast, the best Earth-based telescopes can see stars only about 2 billion light years away. The Space Telescope will be able to point with great accuracy. The data collected by the Space Telescope will be beamed to Earth for analysis.
This area here is called the Observation Support System. What we have are monitors, both color and black and white television displays, which let us see both the science that's coming down from Space Telescope in near real time, and also the monitors up here, which let us check on the health and safety of the telescope and see, in fact, that the proper voltages, the proper temperatures are being maintained by the various subsystems inside the telescope. And here, for example, is an image of a galaxy that has been sent to the Institute. It's possible for an astronomer to zoom or pan across the image, pick out a particular star, for example, if the astronomer wanted to observe that one, send the exact position of the star that he wanted to monitor or study with another instrument back up to the telescope via the TDRSS, the Telemetry Data Relay Satellite, back up to Space Telescope, and that way carry out better observations while sitting here in the Observation Support System.
The Space Telescope will be able to see objects 50 times fainter than those we can see with Earth-based telescopes. It will help scientists to chart the edges of the known universe, to search for clues about the Big Bang theory.
The Space Telescope has been advertised to be able to look almost to the edge of the universe, and in a sense, the universe doesn't have an edge. What I'd like to try and do is explain with a very simple analogy just what that concept means. We think that the universe is expanding. At one time, it was very small. It's getting bigger and bigger as time goes on. And if an astronaut were to start traveling, he would never bump into an edge. There is no edge to the universe, even though the universe has a finite size, and that seems to be contradictory. Well, the simple analogy I can give is at a very early time in the universe, let's picture an ant who starts to crawl around the universe or around the surface of this ball. The ball has a finite size, but the ant never comes to an edge. He never comes to the end. Similarly, if you had an astronaut sitting on top of this expanding universe, or an ant sitting on top of this expanding balloon, as time went on, he'd find himself crawling around and around, and if he crawled long enough, he'd eventually come back to where he started. The universe is the same way. It is finite, and yet it has no boundaries. It has no edges. The expansion of the universe is measured by actually looking at galaxies, measuring how fast they're rushing away from us. That information is sufficient to determine the expansion of the universe. The galaxies act as, in essence, test particles embedded in the universe, kind of like raisins in a raisin cake. And as the raisin cake expands as it's baking, all the raisins move away from each other. Similarly, all the galaxies in the universe are moving away from each other as the universe expands. And by measuring that expansion rate, we can measure first how fast the universe is expanding, and then by measuring how that expansion rate is changing, slowing down, we can see whether the universe will stop expanding eventually and then fall back in on itself.
Astronomers will use the Space Telescope to observe a class of mysterious objects at the far reaches of the universe.
We will, for example, be able to understand for the first time what quasars are. We know that quasars is something that generate an enormous amount of energy. That's why we can see them. But we really don't understand what they are. We think that they are some explosions occurring in the nuclei of galaxies, big galaxies like our Milky Way galaxy. But we can't see the galaxies from the ground because we don't have enough clarity of the pictures. Above the atmosphere, we'll be able to, the first time, resolve that picture, see it sharply, and see whether those quasars are really just explosions at the center of much bigger galaxies.
The Space Telescope will be used for a wide range of different astronomical studies.
My own field of specialty, my own real interest is in cataclysmic binary stars, novas, stars that go bump in the night, stars that suddenly get 100,000 times or even 1,000,000 times brighter than they were the night before and then slowly fade away. Why does this happen? What's the driving mechanism of it? Well, we think we now understand it. They're a kind of colossal hydrogen bomb. If you have two stars that are very close to each other, and one of them is a very, very compact, dense star called a white dwarf, and one is a star somewhat like the sun, the compact, dense star can sometimes cannibalize the other star. It can suck hydrogen off the other star onto its surface. And when it's accumulated about 100,000th of the mass of the sun in hydrogen on its surface, that hydrogen is so compressed and so heated that it explodes like a gigantic hydrogen bomb. That's what makes a nova. But how stars get into that configuration and how they eventually evolve out of it, or how the compact, dense star destroys the other star or eats it away, is a problem that really isn't well understood.
Telescopes may also help us search for extraterrestrial life. To do this, we must look for other planets. But planets are too small to be seen through telescopes. However, a space telescope might be able to spot tiny wobbles in a star's orbit.
One of the hot areas of research in the field of extraterrestrial life right now is the search for a planet around another star. We know we have planets around our star, and we think that other solar-type stars also have planets, but we haven't just actually seen one yet, because it's an extremely difficult observation, right at the limit of our equipment right now. A former PhD student of mine, Bruce Campbell, out at the Dominion Astrophysical Observatory, is actually using the Canada-France-Hawaii telescope with a brand new technique to search for extraterrestrial planets, extrasolar planets around other stars that are like the sun. And he's had some success, some limited success, and it looks like a very promising technique.
What we're attempting to do in this project is to search for very low mass objects that are orbiting stars like the sun. And this could include planetary mass objects. In the case of the solar system, Jupiter is the most massive planet that we know about, but it's still only 1,000th the mass of the sun. If this represents the sun and this is Jupiter, Jupiter goes around the sun in a very large orbit on this scale of order 60 meters or more. However, even though Jupiter is so small, it does influence the sun in that it pulls it around in a wobble, in a counter orbit, as Jupiter goes through its orbit. This motion, of course, is 1,000th that of Jupiter, and that is what we're looking for in other stars, a tiny wobble which would indicate the presence of a hidden body that we can't see directly. The bodies could be as small as Jupiter, could be a planetary-sized object, but we don't know as yet whether that's the correct term for them. Hence, we prefer to call them substellar mass objects.
But perhaps the most important questions the Space Telescope will answer are the ones we haven't even asked yet.
And one of the most exciting things that will come, hopefully, with the Space Telescope is not only things that we talked before about, like understanding quasars and understanding the evolution of the universe and seeing the edge of the universe and the expansion of the universe and so on, but one of the most exciting things almost always happens with new telescope or a new window of the universe are things that we cannot even think about today. Something totally unexpected. We may find some totally unexpected objects out there in the universe that we have never seen before.
The more we see of the universe at a distance, the more we want to see it close up. The urge to explore in person is a fundamental human trait, one that we carry out into space. For now, we can take only the tiniest of steps ourselves, and even our robot emissaries can go a little farther. The Pioneer spacecraft, the first human-made object to leave our neighborhood of planets, has not yet reached the distance of even the nearest star. Perhaps, however, it won't always be that way. NASA sociologist B.J. Bluth describes the vision of one space scientist.
Kraft Ericke was one of the great scientists that came from Germany, space scientists who came from Germany. And he had the concept that evolution didn't happen over long periods of time. It happened in explosive bursts. And that we are now in one of the cracks of those explosive bursts. We're on the edge of the expansion of the humanity into the universe. And this is going to happen very fast. It's not going to happen very slowly. And it's going to accelerate as people move out and as they gain experience and as they see and learn new kinds of things. And it's an imperative for humanity to move off the planet. We really, in many cases, don't have the choice of staying enclosed anymore.
We've seen that the high ground of space gives us a dramatic new perspective. In the process, our perception of the Earth, the planets, the universe, of reality itself has been profoundly altered. And what we see, we want to touch. It's in our nature to want to explore what's over the horizon, to go there ourselves, to go further than we've ever been before. And now, we're poised on the edge of the human expansion into the universe. In the next episode, Outward Bound, we'll look at the magic of space through the art of film and television, painting and storytelling, forms of personal expression that allow all of us to share the space experience.
Discovery Houston, it looks like you're heading toward the right place.
We think so. And Dave, I believe we got a tally ho on it.
Roger that. That sounds pretty good. Old Eagle Eye's up there.
Discovery now within 50 miles from CENTCOM and closing. And the KU band rendezvous radar is activated and has locked on to CENTCOM and is in the passive mode.
And now you're going to close on CENTCOM.
Roger that. We got a bunch of guys looking for it out the top window here.
Discovery has come around into attitude and is now about 331,000 feet from CENTCOM.